Welcome to the Lazy Cosmos, where we explore the universe's biggest mysteries without getting lost in the technical jargon. I'm your cosmic guide, and today we're about to uncover one of astronomy's most profound discoveries: how the spectacular collisions between galaxies are revealing the ultimate fate of everything that exists. If you're ready to discover what the cosmic dance of galaxies tells us about reality itself, hit that subscribe button and let's embark on this mind-bending journey through space and time. Trust me, by the end of this video, you'll never look at the night sky the same way again. Now, before we dive into the mind-bending implications of our cosmic future, we need to completely shatter one of the most common misconceptions about galaxy collisions. When most people hear the phrase galaxy collision, their minds immediately conjure up images of cosmic car crashes, massive explosions, stars smashing into each other like cosmic billiard balls, debris flying everywhere in spectacular fashion. Hollywood has certainly done its part to reinforce this dramatic but completely wrong picture. The reality of galaxy collisions is simultaneously far more subtle and infinitely more fascinating than any special effects team could imagine. Here's the truth that will reshape how you think about the cosmos. Galaxies are mostly empty space, not just a little bit empty. They're so overwhelmingly empty that calling them empty doesn't even do justice to the vast nothingness that dominates their structure. To put this in perspective, let's shrink down our solar system to a scale we can actually comprehend. If we made our sun the size of a grain of sand, just 1 millimeter across, then the nearest star, Proxima Centauri, would be sitting 4 miles away. 4 miles of absolutely nothing but vacuum between two tiny grains of sand. Now imagine that our entire galaxy contains hundreds of billions of these sand grains, each separated by miles and miles of empty space, and you're starting to get a picture of just how much nothingness we're dealing with. When two galaxies approach each other over billions of years, what actually happens is more like watching two enormous swarms of fireflies slowly drifting through each other in a cosmic ballet that unfolds over time frames so vast that human civilization could rise and fall hundreds of times before the dance is complete. The gravitational forces involved are so immense and operate over such colossal distances that individual stars are gently guided into new orbits rather than violently destroyed. It's gravitational choreography on the grandest scale imaginable, where each star follows invisible threads of space-time curvature in an intricate dance that was set in motion billions of years ago. This understanding didn't come easily to humanity. For most of human history, those faint smudges of light visible in telescopes were thought to be nothing more than glowing gas clouds within our own galaxy, what astronomers called spiral nebulae. The idea that these could be entire separate island universes, as some bold theorists suggested, seemed almost too fantastic to believe. After all, if these spiral nebulae were truly distant galaxies, they would have to be unimaginably far away and contain billions upon billions of stars. The implications were staggering and challenged everything we thought we knew about the scale of the universe. Enter Edwin Hubble, a man whose name would become synonymous with our expanding understanding of cosmic scale. In the 1920s, working with the massive 100-inch telescope at Mount Wilson Observatory, the most powerful instrument of its time, Hubble began making observations that would revolutionize our entire conception of reality. He focused on the Andromeda Nebula, that beautiful spiral smudge visible to the naked eye on dark nights, and began looking for something called Cepheid variable stars. These cosmic lighthouses pulse with predictable brightness patterns, and their intrinsic luminosity was well understood, making them perfect cosmic measuring sticks. What Hubble discovered when he found Cepheids in Andromeda changed everything. The stars were so faint that Andromeda had to be incredibly distant, far beyond the boundaries of our own Milky Way galaxy. In one stroke of observational genius, Hubble proved that we lived in a universe filled with countless separate galaxies, each containing billions of stars scattered across distances so vast that light took millions of years to travel between them. The universe had suddenly become a much larger and more magnificent place than anyone had dared to imagine. But Hubble didn't stop there. As he continued his observations of these distant galaxies, he made an even more startling discovery. Not only were we surrounded by countless other galaxies, but these galaxies were moving. Most of them were racing away from us at tremendous speeds, and the farther away they were, the faster they were receding. This observation would lead to the discovery of the expanding universe and eventually to our understanding of the Big Bang itself. However, Hubble also noticed something peculiar about a few nearby galaxies. They weren't moving away from us at all. In fact, some of them, like Andromeda, were actually approaching us. This discovery of approaching galaxies was the first hint that gravity could overcome the cosmic expansion on local scales. While the universe as a whole was expanding, carrying distant galaxies away from us, nearby galaxies remained gravitationally bound together in what we now call galaxy groups and clusters. Our own local group, containing the Milky Way, Andromeda, and dozens of smaller satellite galaxies, represents one of these gravitationally bound islands in the expanding cosmic ocean. The realization that galaxies could influence each other gravitationally opened up entirely new questions about cosmic evolution. If galaxies were moving through space under the influence of gravity, then collisions and interactions were not just possible, they were inevitable. The universe began to look less like a static collection of distant lights and more like a dynamic, ever-changing cosmic ecosystem where galaxies could merge, interact, and transform each other over cosmic time. As astronomers began to study more galaxies in detail, they started finding evidence of these interactions everywhere they looked. Some galaxies had distorted shapes, with long streams of stars extending far beyond their main bodies, like cosmic taffy being pulled apart. Others showed signs of having multiple nuclei, suggesting they were caught in the act of merging with smaller companions. Ring galaxies, peculiar objects with bright rings of star formation surrounding relatively empty centers, appeared to be the aftermath of smaller galaxies punching through the centers of larger ones like cosmic bullets. The physics behind these interactions is both elegant and complex. When two galaxies approach each other, their gravitational fields begin to interact long before the galaxies themselves come into contact. These tidal forces, the same type of gravitational effects that cause ocean tides on Earth, start to distort the shapes of both galaxies, pulling streams of stars out into long, graceful arcs that can extend for hundreds of thousands of light years. The dark matter halos that surround each galaxy, invisible but containing most of each galaxy's mass, begin their own gravitational dance, ultimately determining the final outcome of the encounter. What makes these galactic encounters so fascinating is their incredible duration. A typical galaxy collision unfolds over hundreds of millions to billions of years, time frames so vast that they dwarf all of human history. Stars born at the beginning of a galactic merger might live their entire lives, die, and have their stellar remnants orbit for eons before the merger is complete. From the perspective of any hypothetical civilizations living through such an event, the process would be so gradual as to be nearly imperceptible, visible only through careful astronomical observations spanning many generations. The outcomes of these cosmic encounters depend on numerous factors: the masses of the galaxies involved, their relative speeds, the angles of their approaches, and the distribution of dark matter in their halos. A small galaxy encountering a much larger one might be completely disrupted, its stars scattered throughout the larger galaxy's halo like cosmic seasoning. Two galaxies of similar mass, however, can engage in a more prolonged dance, orbiting each other multiple times over billions of years before finally settling into a new, merged configuration. Perhaps most remarkably, computer simulations have shown us that these galaxy mergers often trigger spectacular bursts of star formation. As gas clouds within the merging galaxies collide and compress, they reach the densities needed to ignite new generations of stars. These starburst galaxies can form new stars at rates hundreds of times faster than normal, illuminating the cosmic collision with the brilliant light of billions of newborn suns. The merger process doesn't just rearrange existing stars, it actively creates new ones, extending the universe's stellar lifetime and ensuring that the cosmic recycling program continues. The supermassive black holes that lurk at the centers of most large galaxies also participate in this cosmic dance. As galaxies merge, their central black holes spiral inward toward each other, eventually forming binary systems that orbit ever closer until they finally merge in cataclysmic events that send ripples through spacetime itself. These gravitational waves, recently detected by instruments like LIGO, represent some of the most violent events in the universe, the final moments of black hole mergers that release more energy in gravitational waves than all the stars in the observable universe emit in light. Understanding galaxy collisions has also revealed crucial insights about the mysterious dark matter that dominates the universe's mass. When galaxies collide, the behavior of visible matter, stars and gas, can be quite different from the behavior of dark matter. Visible matter can experience friction and electromagnetic interactions that slow it down during collisions, while dark matter passes through essentially unimpeded. This difference in behavior has been observed directly in colliding galaxy clusters, providing some of our best evidence for dark matter's existence and properties. The Bullet Cluster, a spectacular collision between two galaxy clusters, serves as a perfect example of this phenomenon. When these massive collections of galaxies collided, the hot gas between the galaxies was slowed down by electromagnetic interactions, while the dark matter continued moving at its original speed. Gravitational lensing observations revealed that most of the mass, the dark matter, had separated from the visible matter, providing compelling evidence that dark matter truly exists as a separate component of the universe. As we've developed more sophisticated computer models and observational techniques, our understanding of galaxy collisions has become incredibly detailed. Modern simulations can follow the evolution of individual star particles through billion-year mergers, predicting not just the final shapes of merged galaxies, but also the detailed properties of the stars that will populate them. These models have revealed that galaxy mergers are not random, chaotic events, but follow predictable patterns determined by the fundamental laws of physics and the initial conditions of the colliding systems. This deep understanding of galactic interactions has profound implications for our comprehension of cosmic evolution. Galaxy collisions aren't just interesting astronomical phenomena. They're fundamental processes that have shaped the universe we see today. Most of the massive elliptical galaxies that dominate galaxy clusters appear to be the products of ancient mergers between smaller spiral galaxies. The Milky Way itself bears the scars of past encounters, with streams of stars from disrupted satellite galaxies still visible in our galaxy's halo, telling the story of cosmic cannibalism that has continued for billions of years. The cosmic dance of galaxies thus represents far more than just a beautiful astronomical phenomenon. It's a window into the fundamental processes that govern cosmic evolution, a laboratory for studying dark matter and dark energy, and a preview of our own cosmic future. As we've learned to decode the gravitational choreography of these cosmic ballets, we've gained unprecedented insights into the nature of space, time, gravity, and the ultimate fate of everything we can see. The dance that began with the first gravitational collapse in the early universe continues today and will determine the final chapters of cosmic history billions of years from now. The launch of the Hubble Space Telescope in 1990 marked a revolutionary turning point in our understanding of galaxy collisions, transforming what had been largely theoretical concepts into stunning visual reality. For the first time in human history, we could peer deep into space with unprecedented clarity, free from the blurring effects of Earth's atmosphere, and witness the cosmic dance of galaxies in exquisite detail. What Hubble revealed was beyond anything astronomers had dared to imagine. A universe filled with galactic interactions so beautiful and complex that they challenged our understanding of how cosmic structures form and evolve. Before Hubble, galaxy collisions were mostly studied through ground-based telescopes that struggled to capture fine details through the turbulent atmosphere. Astronomers could see that some galaxies had unusual shapes or disturbed structures, but the intricate details of gravitational interactions remained hidden. When Hubble began transmitting its crystal-clear images back to Earth, it was like suddenly being able to see the individual brushstrokes in a cosmic masterpiece that had previously appeared as just blurry smudges of light. One of the most spectacular examples of galactic interaction that Hubble revealed is the pair known as the Antennae Galaxies, located about 45 million light-years away in the constellation Corvus. These two spiral galaxies began their cosmic dance about 600 million years ago, and Hubble's images show them locked in a gravitational embrace that has dramatically transformed both systems. The galaxies get their name from the two long streams of stars, gas, and dust that extend from their main bodies like the antennae of an insect, stretching across hundreds of thousands of light-years of space. These graceful arcs aren't random. They're precisely sculpted by gravitational forces, with computer simulations showing exactly how tidal forces can pull streams of stars out of their parent galaxies during close encounters. What makes the Antennae Galaxies particularly fascinating is that they're caught in the act of creating new stars at a prodigious rate. Hubble's detailed observations revealed over 1,000 brilliant star-forming regions scattered throughout the merging system, each one a stellar nursery where gas clouds compressed by the collision are giving birth to new generations of stars. Some of these star formation regions are so massive and luminous that they outshine entire normal galaxies, creating what astronomers call superstar clusters, collections of millions of young hot stars packed into regions just a few light years across. The collision has also triggered the formation of massive young star clusters that will eventually evolve into globular clusters, those ancient stellar cities that orbit around most large galaxies. By studying the antennae, astronomers realize that galaxy mergers might be responsible for creating many of the globular clusters we see throughout the universe, solving a long-standing mystery about how these ancient stellar populations formed. Another remarkable system that Hubble brought into sharp focus is the pair known as the Mice galaxies, officially designated NGC 4676. Located about 300 million light-years away, these two spiral galaxies are engaged in their own gravitational ballet, creating some of the most dramatic tidal tales ever observed. The galaxies get their whimsical name from the long, curved streams of stars that extend behind each galaxy like mouse tails, stretching across nearly 500,000 light-years of space. These tails contain billions of stars that have been gravitationally pulled from their parent galaxies during the encounter. What's particularly striking about the mice is how the collision has affected their internal structure. Hubble's images reveal that the gravitational interaction has triggered intense star formation in both galaxies, creating brilliant blue regions where massive young stars are being born. The encounter has also distorted the spiral arms of both galaxies, creating complex patterns of dust lanes and stellar streams that tell the detailed story of their gravitational interaction. Computer simulations of the Mice galaxies have been particularly successful in reproducing the observed structures, confirming our understanding of how gravity sculpts these cosmic encounters. The models show that the two galaxies made their closest approach about 160 million years ago, and they're now slowly separating before gravity pulls them back together for a final merger in about 1 billion years. When that happens, the two spiral galaxies will transform into a single, massive elliptical galaxy, erasing their individual identities in favor of a new cosmic entity. Perhaps one of the most spectacular examples of multiple galaxy interactions that Hubble has documented is Stephan's quintet, a visual grouping of 5 galaxies in the constellation Pegasus. This system, first discovered in 1877, became one of Hubble's most famous targets because it showcases multiple types of galactic interactions occurring simultaneously. 4 of the 5 galaxies are actually interacting gravitationally, located about 290 million light-years away, while the 5th is much closer and appears in the group only by chance alignment. Stephan's quintet demonstrates how galaxy groups can experience complex, multi-body interactions over cosmic time. Hubble's detailed observations reveal shock waves propagating through the intergalactic medium as galaxies sweep through the shared space, heating gas to millions of degrees and triggering star formation throughout the system. The interactions have stripped gas and stars from the individual galaxies, creating a complex web of tidal debris that connects all the group members. The system also contains one of the largest shock waves ever observed in space, created when one of the galaxies plowed through the group at high speed. The collision compressed and heated the intergalactic gas, creating a shock front that spans hundreds of thousands of light years and glows brilliantly in certain wavelengths of light. Studying these shock waves helps astronomers understand how galaxy collisions can affect not just the galaxies themselves, but the entire environment around them. While these distant examples of galaxy collisions provide spectacular case studies, perhaps the most personally relevant discovery that modern astronomy has made concerns our own cosmic neighborhood. Detailed measurements of the Andromeda Galaxy's motion, made possible by combining Hubble observations with ground-based telescopes, have revealed that our nearest major galactic neighbor is on a direct collision course with the Milky Way. This discovery represents one of the most certain predictions about the far future that science has ever made. The story of discovering Andromeda's approach began in the early 20th century when astronomers first measured its radial velocity, how fast it was moving toward or away from us along our line of sight. They found that Andromeda was approaching at about 250,000 miles per hour, but this measurement alone wasn't enough to predict whether a collision would occur. The galaxy might be moving toward us, but also sideways, in which case it could pass by the Milky Way without a direct encounter. The breakthrough came when Hubble's incredible precision allowed astronomers to measure Andromeda's proper motion, its movement across the sky, perpendicular to our line of sight. This required observing the positions of stars within Andromeda with such accuracy that the entire galaxy's motion could be detected despite its enormous distance of 2.5 million light-years. The measurements took years to complete because the motion is incredibly small from our perspective, but the results were definitive. Andromeda is heading straight for us with minimal sideways motion. Computer simulations using these precise measurements have mapped out our galactic future in extraordinary detail. In approximately 4.5 billion years, Andromeda will make its closest approach to the Milky Way, and the two galaxies will begin a complex gravitational dance that will last for several billion years. The initial encounter will distort both galaxies dramatically, flinging streams of stars into intergalactic space and triggering massive bursts of star formation as gas clouds collide and compress. What's remarkable is how detailed these predictions have become. Simulations can track the likely fate of our solar system during the merger, suggesting that we'll probably be flung outward to a more distant orbit in the merged galaxy, now nicknamed Milkomeda by astronomers. The night sky as seen from Earth will be transformed beyond recognition, with the merged galaxy's central regions creating a brilliant band of stars across the heavens that will dwarf anything visible in today's night sky. The merger will also profoundly affect star formation in both galaxies. The Milky Way and Andromeda currently form new stars at relatively modest rates, but the collision will compress vast reservoirs of gas, triggering a starburst that could increase star formation rates by factors of 10 or more. This burst of stellar birth will be visible from billions of light-years away, making Milkomeda temporarily one of the most luminous galaxies in our cosmic neighborhood. The parallel development of computer simulations has been crucial to our understanding of these cosmic events. Starting in the 1970s, astronomers began using the first generation of supercomputers to model galaxy collisions, initially with just a few thousand particles representing stars and dark matter. These early simulations were crude by today's standards, but provided the first insights into how gravitational interactions could create the structures we observe. As computing power increased exponentially over the following decades, simulations became increasingly sophisticated. Modern galaxy merger simulations can track millions or even billions of particles, representing not just stars and dark matter, but also the complex behavior of gas clouds that respond to both gravity and electromagnetic forces. These simulations can model the formation of new stars during mergers, the growth of supermassive black holes, and the detailed evolution of galaxy shapes over billions of years. The Millennium simulation, completed in 2005, represented a landmark achievement in computational cosmology. This massive calculation followed the evolution of over 10 billion dark matter particles in a cube of space 2 billion light-years on a side, from the early universe to the present day. For the first time, astronomers could watch the entire cosmic web form in a computer simulation, seeing how dark matter halos merge and grow over cosmic time, eventually becoming the scaffolding on which galaxies form. These simulations revealed that galaxy mergers aren't random events, but follow predictable patterns determined by the underlying dark matter structure of the universe. Small galaxies merge to form larger ones in a hierarchical process that continues throughout cosmic history. The simulations showed that most large elliptical galaxies are likely the products of major mergers between spiral galaxies, while smaller interactions can trigger star formation and reshape galactic structures without completely destroying the original spiral patterns. The agreement between observations and simulations has become remarkably precise. When astronomers discover a new example of interacting galaxies, they can often create detailed computer models that reproduce the observed structures with stunning accuracy. This success gives us confidence that our understanding of gravitational physics and galaxy evolution is fundamentally correct, even when dealing with systems so complex that they contain hundreds of billions of individual stars. Modern simulations have also revealed the crucial role of dark matter in determining merger outcomes. The dark matter halos that surround galaxies contain most of their mass and largely determine how galactic encounters will proceed. When two galaxies approach each other, their dark matter halos begin interacting first, creating the gravitational framework within which the visible matter, stars and gas, will evolve. Understanding this invisible choreography has been essential to making sense of the complex structures we observe in colliding galaxy systems. The combination of Hubble's observational capabilities and increasingly powerful computer simulations has transformed galaxy collisions from mysterious, poorly understood phenomena into precisely modeled physical processes. We can now predict the outcomes of galactic encounters with remarkable accuracy, trace the evolutionary history of individual galaxies by analyzing their current structures, and even forecast the detailed future evolution of our own cosmic neighborhood. This revolution in understanding has profound implications for our comprehension of cosmic evolution. Galaxy mergers emerged not as rare, catastrophic events, but as fundamental processes that have shaped the universe throughout cosmic history. The beautiful, complex structures that Hubble reveals in interacting galaxies represent snapshots of ongoing cosmic evolution, frozen moments in gravitational ballets that unfold over billions of years and will ultimately determine the final architecture of the universe itself. To truly understand how galaxy collisions reveal the universe's future, we need to dive into one of the most profound mysteries in all of science, a mystery that was first glimpsed by a brilliant but eccentric astronomer working in the 1930s, decades before anyone realized they were looking at evidence for something that would completely revolutionize our understanding of reality itself. This is the story of dark matter, the invisible cosmic scaffolding that makes up 85% of all matter in the universe, and how galaxy collisions became our most powerful tool for detecting and understanding this ghostly substance that shapes everything we see. The story begins with Fritz Zwicky, a Swiss-American astronomer working at the California Institute of Technology, who had a reputation for being both incredibly insightful and somewhat difficult to work with. Zwicky was studying the Coma Cluster, a massive collection of over 1,000 galaxies located about 320 million light-years from Earth, when he noticed something that seemed completely impossible according to everything astronomers thought they knew about how the universe worked. The galaxies within the cluster were moving far too fast, so fast that they should have escaped the cluster's gravitational pull eons ago and scattered into the cosmic void. Using the best measurements available in 1933, Zwicky calculated that the total mass of all the visible stars in the Coma cluster should only be about to hold together a system where galaxies moved at much slower speeds. Yet observations clearly showed galaxies zipping through the cluster at velocities that required the gravitational influence of something with far more mass than all the visible stars combined. Zwicky concluded that there had to be enormous amounts of missing mass hidden within the cluster, matter that was completely invisible to telescopes, but whose gravitational effects were undeniably real. At the time, Zwicky's discovery was largely ignored by the astronomical community. The idea that most of the universe could be made of invisible matter seemed too radical, too impossible to take seriously. After all, if matter existed in such enormous quantities, why couldn't anyone see it? Zwicky called this mysterious substance Dunkel Materie, dark matter, and moved on to other research, leaving the mystery unsolved for nearly 4 decades. The breakthrough that would eventually vindicate Zwicky's insights came in the 1970s through the meticulous work of astronomer Vera Rubin at the Carnegie Institution for Science. Rubin was studying something much more local than galaxy clusters. She was looking at how individual galaxies rotate, measuring the speeds of stars and gas clouds at various distances from galactic centers. According to everything astronomers understood about orbital mechanics, stars farther from a galaxy's center should move more slowly, just as outer planets in our solar system take longer to complete their orbits than inner planets. What Rubin discovered was shocking. Instead of slowing down with distance from the galactic center, stars in the outer regions of spiral galaxies maintain nearly constant orbital speeds, even at the very edges where very few stars were visible. This observation, now known as the flat rotation curve problem, indicated that galaxies contained vast amounts of invisible matter distributed throughout enormous spherical halos extending far beyond the visible stellar disks. Rubin's rotation curve measurements provided the smoking gun evidence that dark matter wasn't just present in massive galaxy clusters, but was a fundamental component of individual galaxies throughout the universe. Her work showed that every large galaxy must be embedded within a massive halo of dark matter that contains several times more mass than all the visible stars combined. Without this invisible scaffolding, galaxies would simply fly apart, unable to maintain their coherent structure over cosmic time. But dark matter remained frustratingly elusive. It didn't emit, absorb, or reflect electromagnetic radiation of any kind, making it completely invisible to all conventional astronomical observations. Scientists could detect its gravitational effects but had no way to study its properties directly. Dark matter was like a cosmic ghost, undeniably present, but impossible to see. That's where galaxy collisions entered the story and transformed our understanding of this mysterious substance. When galaxies collide, something remarkable happens that allows us to separate the behavior of dark matter from the behavior of ordinary matter in ways that would be impossible to observe under normal circumstances. During a galactic collision, the visible matter, stars, gas, and dust, can experience electromagnetic interactions and friction effects that slow down its motion, while dark matter, which interacts only through gravity, passes through essentially unimpeded. This difference in behavior during collisions provides a unique window into dark matter's properties and distribution. The most spectacular demonstration of this phenomenon occurred in a system called the Bullet Cluster, located about 3.7 billion light-years away in the constellation Carina. The Bullet Cluster represents the aftermath of a collision between two massive galaxy clusters, each containing hundreds of galaxies and vast amounts of hot gas in the space between them. When these two clusters collided at speeds of several million miles per hour, something extraordinary happened that provided the most direct evidence for dark matter's existence that astronomers had ever obtained. During the collision, the hot gas that fills the space between galaxies in each cluster experienced tremendous electromagnetic forces as it encountered gas from the opposing cluster. This interaction created friction and shock waves that dramatically slowed down the gas, causing it to lag behind the galaxies themselves, which experienced only gravitational interactions during the encounter. The result was a clear spatial separation between the visible matter, which had been slowed by electromagnetic interactions, and the dark matter, which had passed through the collision largely unaffected. What makes the Bullet Cluster so compelling as evidence for dark matter is that astronomers can actually map the distribution of mass in the system using a technique called gravitational lensing. According to Einstein's theory of general relativity, massive objects bend the fabric of spacetime, and this curvature deflects light rays passing through the region. When astronomers look at distant galaxies located behind the Bullet Cluster, they see these background galaxies distorted and magnified by the gravitational lensing effect of the cluster's mass. By carefully analyzing these lensing distortions, astronomers can create detailed maps showing exactly where the mass is located in the Bullet Cluster system, regardless of whether that mass is visible or invisible. What they found was revolutionary. The majority of the mass in the system was located with the galaxies themselves, not with the hot gas that had been slowed by the collision. This meant that most of the matter in the cluster was dark matter that had passed right through the collision without being affected by electromagnetic forces. The Bullet Cluster observations provided the most direct evidence that dark matter truly exists as a separate component of the universe, distinct from ordinary matter. The clear spatial separation between the visible gas and the invisible mass ruled out alternative theories that tried to explain galactic rotation curves by modifying our understanding of gravity rather than invoking invisible matter. Here was a system where you could literally see the effects of dark matter behaving differently from ordinary matter during a cosmic collision. But the Bullet Cluster was just the beginning. As astronomers studied more colliding galaxy systems, they found similar evidence for dark matter's unique behavior during galactic encounters throughout the universe. Each collision provided new insights into dark matter's properties and distribution, gradually building up a comprehensive picture of how this invisible substance shapes cosmic evolution. Galaxy collisions also revealed the crucial role that dark matter halos play in determining the outcomes of galactic encounters. When two galaxies approach each other, their dark matter halos begin interacting long before the visible components come into contact. These halos, which can extend several times farther than the visible galaxy disks, contain most of each galaxy's mass and therefore dominate the gravitational dynamics of the collision. Computer simulations of galaxy mergers must include detailed models of dark matter halo interactions to accurately reproduce observed collision outcomes. These simulations have shown that the masses and internal structures of dark matter halos largely determine whether a galactic encounter will result in a major merger, a minor interaction that strips away satellite galaxies, or a high-speed flyby that leaves both systems largely intact. The discovery that dark matter halos govern galaxy collision outcomes has profound implications for understanding cosmic evolution. Throughout the universe's history, the growth and merger of dark matter halos has provided the gravitational framework within which galaxies form and evolve. Small, dark matter halos merge to form larger ones in a hierarchical process that continues throughout cosmic time, and each halo merger potentially triggers the formation or transformation of the galaxies embedded within them. This understanding has led to a completely new picture of cosmic evolution, where dark matter provides the invisible architecture that determines when and where galaxy formation occurs. In the early universe, the first dark matter halos to collapse gravitationally became the sites where the first stars and galaxies formed. As these halos grew through mergers with neighboring halos, they triggered successive generations of galaxy formation and evolution. Modern astronomical surveys have revealed the cosmic web, a vast network of dark matter filaments connecting massive nodes where galaxy clusters form. This invisible scaffolding, traced out by the distribution of galaxies throughout space, represents the underlying dark matter structure that has guided cosmic evolution since the early universe. Galaxy collisions occur preferentially along these filaments and at the nodes where they intersect, reflecting the fundamental role that dark matter plays in organizing cosmic structure. The study of galaxy collisions has also revealed that dark matter halos have complex internal structures that affect how galaxies interact. Dense central regions, called cusps, can survive galactic encounters largely intact, while more diffuse outer regions can be stripped away during close passages. These interactions redistribute dark matter throughout galaxy groups and clusters, gradually building up the massive halos that dominate the most massive cosmic structures. Perhaps most remarkably, galaxy collisions have provided insights into the fundamental physics of dark matter itself. By studying how dark matter behaves during collisions, astronomers can test different theoretical models for what dark matter might be. If dark matter particles could interact with each other through forces other than gravity, these interactions might become detectable during the extreme conditions of galaxy cluster collisions. So far, observations of colliding systems like the Bullet Cluster suggest that dark matter is collisionless, meaning that dark matter particles pass through each other without significant interactions beyond their gravitational attraction. This property helps narrow down the possibilities for what dark matter might be, ruling out some theoretical candidates while supporting others, like weakly interacting massive particles that could be detected in underground laboratory experiments. The role of dark matter in galaxy collisions also has direct implications for understanding our own cosmic future. When the Milky Way and Andromeda galaxies collide in about 4.5 billion years, the outcome will be largely determined by the properties and interactions of their respective dark matter halos. Computer simulations of this future merger must include detailed models of how these invisible halos will merge and reshape, as the behavior of the dark matter will ultimately determine the final structure of the merged galaxy system. As we've learned to decode the gravitational signatures of dark matter through galaxy collisions, we've gained unprecedented insights into the fundamental composition of the universe. What began as Fritz Zwicky's puzzling observations of missing mass in galaxy clusters has evolved into a comprehensive understanding of how invisible matter provides the cosmic scaffolding that shapes everything we see. Galaxy collisions have transformed from spectacular but poorly understood phenomena into precision tools for studying the most mysterious component of the universe, revealing that the cosmic dance of galaxies is choreographed by forces and matter that remain completely hidden from our direct view, but whose effects determine the ultimate fate of cosmic structure itself. This invisible choreographer, dark matter, doesn't just passively provide gravitational scaffolding for galaxy formation and evolution. Through galaxy collisions, we've learned that dark matter actively shapes cosmic history, determining which galaxies will merge, when star formation will be triggered, and how the large-scale structure of the universe will continue to evolve over billions of years to come. Now we arrive at one of the most mind-bending paradoxes in all of cosmology, a cosmic contradiction that seems to defy logic and challenges our basic understanding of how the universe works. On one hand, we know with absolute certainty that the universe is expanding, carrying distant galaxies away from us at ever-increasing speeds in a process that began with the Big Bang nearly 14 billion years ago. On the other hand, we've just seen how galaxies like Andromeda are actually moving toward us, destined for spectacular collisions that will reshape the cosmic landscape. How can both of these seemingly contradictory facts be true simultaneously? The answer to this paradox reveals some of the deepest truths about the nature of space, time, and the ultimate fate of everything that exists. The story begins with Edwin Hubble's revolutionary discovery in the 1920s that fundamentally changed our understanding of the cosmos. When Hubble measured the distances and velocities of galaxies throughout the observable universe, he uncovered a relationship so simple and yet so profound that it transformed our entire conception of reality. The farther away a galaxy was located, the faster it was moving away from us. This relationship, now known as Hubble's law, revealed that space itself was expanding uniformly in all directions, carrying galaxies along like raisins in rising bread dough. The implications of this discovery were staggering. If the universe was expanding today, then it must have been smaller in the past. Tracing this expansion backward in time led inevitably to the conclusion that the entire observable universe must have emerged from an incredibly hot, dense state, the Big Bang, approximately 13.8 billion years ago. The expansion wasn't the result of galaxies moving through static space, but rather the stretching of space itself, creating new distance between cosmic objects as time progressed. Hubble's observations showed that this cosmic expansion follows a precise mathematical relationship. Galaxies twice as far away are moving away twice as fast. Galaxies 3 times as far away are receding 3 times as fast, and so on. This proportional relationship means that from any vantage point in the universe, every other location appears to be moving away, creating the illusion that you're at the center of expansion when in reality there is no center. The expansion is happening everywhere simultaneously. But here's where the paradox becomes apparent. If space is expanding and carrying all galaxies away from each other, why are some galaxies, like Andromeda, actually approaching us? Why do galaxy collisions happen at all in an expanding universe? The answer lies in understanding that cosmic expansion and gravitational attraction operate on completely different scales and follow different rules, creating a cosmic tug-of-war whose outcome depends on the specific circumstances of each region of space. The key to resolving this apparent contradiction lies in recognizing that gravity can overcome cosmic expansion on relatively small scales. And by small, we mean anything up to the size of galaxy groups and clusters, which can span tens of millions of light years. While the universe expands on the largest scales, carrying distant galaxy clusters away from each other, gravity remains the dominant force within these clusters and groups, holding their member galaxies together, and sometimes pulling them into collision courses. Our own cosmic neighborhood provides a perfect example of this principle in action. The Milky Way, Andromeda, and about 50 smaller galaxies form what astronomers call the local group, a gravitationally bound collection of galaxies spanning roughly 10 million light-years across. Within this local group, the combined gravitational pull of all the member galaxies is strong enough to overcome the cosmic expansion, keeping the group bound together as a coherent unit, even as the universe expands around us. Think of it this way. Imagine you're standing on a moving walkway at an airport, but instead of moving at a steady speed, the walkway is accelerating and stretching as you stand on it. If you and a friend are standing close together on this stretching walkway, you can still reach out and grab each other's hands despite the walkway's motion. But someone standing far away on the same walkway will be carried away from you faster than you could possibly run to catch them. This is essentially what's happening in the universe. Gravity can still pull together nearby objects, but cosmic expansion wins out over vast distances. The local group is held together by the combined gravitational influence of its most massive members, primarily the Milky Way and Andromeda galaxies. Each of these spiral giants contains hundreds of billions of stars and is embedded within a massive dark matter halo that extends far beyond the visible galaxy disk. The gravitational pull of these dark matter halos dominates the dynamics of the entire local group, determining the orbits and eventual fates of all the member galaxies. This is why Andromeda is approaching us despite cosmic expansion. The gravitational attraction between the Milky Way and Andromeda is strong enough to overcome the expansion of space on the scale of the local group. Rather than being carried apart by expansion, these two galaxies are falling toward each other under their mutual gravitational influence, destined for a collision that will occur in roughly 4.5 billion years. But step outside the local group, and the situation changes dramatically. The next major galaxy group, the Virgo cluster, located about 65 million light-years away, is receding from us due to cosmic expansion. While we can still detect the gravitational influence of this massive cluster, it's actually pulling the entire local group toward it at several hundred kilometers per second. The expansion of space between us and Virgo is winning the tug-of-war, carrying the cluster away from us over cosmic time. This transition from gravitationally bound to expansion-dominated behavior occurs at what astronomers call the turnaround radius, the distance at which the expansion of space exactly balances gravitational attraction. Objects closer than this radius will eventually fall together and merge, while objects farther away will be carried apart by expansion and never interact again. For massive galaxy clusters, this radius can extend to 20 million light-years or more, while for smaller galaxy groups like our local group, it's considerably smaller. Understanding this balance between expansion and gravity has profound implications for predicting the universe's future evolution. The ultimate fate of cosmic structure depends on several fundamental properties of the universe, including its total density, the nature of dark matter, and the mysterious force known as dark energy that appears to be accelerating the cosmic expansion. In the 1990s, astronomers studying distant supernovae made one of the most shocking discoveries in the history of science. Rather than finding that cosmic expansion was slowing down due to gravitational attraction, as most theories predicted, they found that the expansion was actually speeding up. Something was counteracting gravity on the largest scales, pushing space apart with ever-increasing vigor. This mysterious force or property of space itself became known as dark energy, and it appears to make up roughly 68% of the total energy content of the universe. Dark energy's accelerating expansion creates a cosmic race between expansion and gravity that will ultimately determine the fate of all structure in the universe. Currently, dark energy's influence is relatively weak on the scales of galaxy groups and clusters, allowing gravity to continue forming new-bound structures through ongoing mergers and accretion. But as the universe continues to expand and the density of matter decreases, dark energy's influence becomes increasingly dominant. The critical question for the universe's future is whether dark energy will remain constant, increase, or decrease over cosmic time. If dark energy remains at its current strength, it will gradually win the tug-of-war against gravity on larger and larger scales. Galaxy clusters that are currently bound together will eventually be stretched apart as the space between them expands faster than gravity can pull them together. In this scenario, the local group and other nearby galaxy groups represent islands of structure that will remain gravitationally bound while becoming increasingly isolated from the rest of the universe. If dark energy continues to strengthen over time, as some theoretical models suggest, the consequences become even more dramatic. In the most extreme scenario, known as the Big Rip, dark energy could eventually become so dominant that it overcomes gravity on all scales, tearing apart galaxy clusters, individual galaxies, solar systems, and ultimately even atoms themselves as the expansion of space accelerates without limit. The current observational evidence suggests that dark energy has remained roughly constant throughout cosmic history, but the measurements are still not precise enough to rule out slowly changing dark energy. Understanding the nature and evolution of dark energy has become one of the highest priorities in modern cosmology, as it will determine whether the universe's future holds continued structure formation or the gradual dissolution of all gravitationally bound systems. This cosmic battle between expansion and gravity also helps explain the observed history of galaxy formation and evolution. In the early universe, when matter was much denser and dark energy's influence was weaker, gravity had a much easier time overcoming expansion to form the first stars, galaxies, and galaxy clusters. The peak epoch of galaxy formation occurred roughly 8 to 10 billion years ago, when the universe was about half its current age and significantly denser than today. Since that cosmic noon, the formation of new massive galaxies has slowed dramatically as expanding space has made it increasingly difficult for gravity to assemble new large-scale structures. Most of the massive elliptical galaxies we observe today are thought to have formed through major mergers during this earlier epoch, when galaxy collisions were much more common than they are now. The decreasing merger rate over cosmic time reflects this ongoing competition between expansion and gravity. As the universe ages and expands, galaxy groups become increasingly isolated from each other, making new encounters between different groups less and less likely. Within existing groups and clusters, mergers continue to occur as smaller galaxies are gradually absorbed by larger ones, but the formation of entirely new, massive systems becomes progressively more difficult. This evolution has profound implications for the long-term future of star formation throughout the universe. Galaxy mergers trigger bursts of star formation by compressing gas clouds and feeding new material to galaxy centers. As merger rates decline due to cosmic expansion, the overall rate of star formation throughout the universe is also declining. We're already past the peak of cosmic star formation, entering an era where the birth of new stars will become increasingly rare. The interplay between cosmic expansion and gravitational attraction also affects the evolution of the cosmic web. The largest scale structure in the universe consisting of filaments of dark matter connecting massive nodes where galaxy clusters form. Computer simulations show that this web-like structure will continue to evolve as expansion stretches the filaments and isolates the nodes, gradually transforming the universe from a connected network of structure into isolated islands separated by ever-increasing voids. Within our own cosmic neighborhood, the victory of gravity over expansion within the local group ensures that the Milky Way Andromeda collision will proceed as predicted. But this merger will likely be one of the last major galaxy formation events in our region of the universe. After Milkomeda forms, there will be no other major galaxies close enough to provide material for future mergers, as cosmic expansion will have carried all other galaxy groups beyond our gravitational reach. The cosmic expansion also determines the ultimate observational horizon for future astronomers. As expansion continues to accelerate, distant galaxies will be carried away from us so rapidly that their light will become increasingly redshifted and faint. Eventually, even the most powerful telescopes will lose sight of the most distant galaxies as they cross beyond our observable horizon. Future civilizations in Milkomeda may find themselves in a universe that appears to contain only their own merged galaxy, with no evidence remaining of the cosmic expansion or the Big Bang that created everything they see. This cosmic race between expansion and gravity represents one of the fundamental processes shaping the universe's evolution from the Big Bang to its ultimate fate billions of years in the future. Galaxy collisions serve as both a consequence of this competition and a tool for understanding it, revealing how the balance between attractive and repulsive forces determines the formation, evolution, and eventual dissolution of all cosmic structure. The beautiful spiral galaxies, dramatic merger events, and complex cosmic web we observe today represent temporary victories of gravity over expansion, islands of structure in an increasingly empty universe that will ultimately be shaped by the mysterious dark energy that continues to accelerate the cosmic expansion toward an uncertain but inevitable future. Here's where our story takes a truly extraordinary turn. Because galaxy collisions aren't just spectacular cosmic events happening in isolation. They're actually cosmic timepieces, revealing the universe's entire evolutionary history and allowing us to predict its future with stunning precision. By studying when galaxy mergers occurred most frequently, how often they happen now, and how their rates have changed over billions of years, astronomers have essentially decoded the universe's biography, written in the gravitational interactions between cosmic islands of stars. What this cosmic timeline reveals is both beautiful and sobering. We're living in a universe that has already passed its prime, entering a long twilight phase that will ultimately lead to cosmic loneliness on scales almost impossible to imagine. The story of cosmic evolution through galaxy collisions begins in the early universe, roughly 13 billion years ago, when the cosmos was a very different place than the universe we observe today. In those ancient epochs, the universe was much smaller, denser, and more chaotic than anything we see in the modern cosmos. Galaxies were packed much closer together. Dark matter had not yet had time to settle into the smooth, large-scale structures we observe today, and the very concept of stable galactic neighborhoods like our local group didn't exist. Instead, the early universe was a cosmic construction zone where galaxy formation and destruction happened at a breakneck pace through constant mergers and interactions. During this primordial era, small protogalaxies, the building blocks of today's massive spiral and elliptical systems, were colliding and merging at rates that dwarf anything we observe in the contemporary universe. These weren't the gentle billion-year dances we see today between mature galaxies like the Milky Way and Andromeda. Instead, they were rapid-fire encounters between relatively small, gas-rich systems that would completely transform with each collision, building up mass and complexity through a process astronomers call hierarchical assembly. The peak of this cosmic construction phase occurred roughly 8 to 10 billion years ago, during an epoch that astronomers have dubbed cosmic noon. This wasn't just a poetic name. It represents the actual high point of cosmic activity, when galaxy formation, star creation, and merger activity all reach their maximum rates. During cosmic noon, galaxy collision rates were roughly 10 times higher than what we observe today, and the universe was forming new stars at rates that make modern galactic star formation look practically dormant by comparison. What makes cosmic noon so significant is that most of the massive elliptical galaxies we see throughout the universe today were assembled during this epoch through major mergers between spiral galaxies. The beautiful spiral structure that we see in galaxies like the Milky Way and Andromeda is relatively fragile and can be completely destroyed during major mergers, with the stellar disks being scrambled into the more chaotic, roughly spherical distributions of stars that characterize elliptical galaxies. The abundance of massive elliptical galaxies in today's universe serves as fossil evidence for the intense merger activity that occurred during cosmic noon. Computer simulations of cosmic evolution have revealed the detailed timeline of how this merger activity has evolved over the universe's 13.8 billion year history. In the first few billion years after the Big Bang, Small dark matter halos were constantly merging to form larger and larger structures, and each halo merger potentially triggered the formation or growth of galaxies within those halos. The merger tree, a branching diagram showing how cosmic structures grow through successive mergers, resembles an upside-down family tree, with countless small branches at the top representing early small-scale mergers, gradually combining into fewer and fewer massive branches representing the large-scale structures we see today. This hierarchical assembly process means that every galaxy we observe today, including our own Milky Way, contains the remnants of dozens or even hundreds of smaller galaxies that were consumed during the cosmic construction phase. When astronomers study the outer halos of large galaxies in detail, they can actually see the ghostly streams of stars left behind by these ancient merger events, like cosmic archaeological evidence of our galaxy's cannibalistic past. The Milky Way's halo contains multiple stellar streams from disrupted satellite galaxies, each one telling the story of a smaller galaxy that was torn apart and consumed during our galaxy's growth phase. The transition from cosmic noon to the present day represents one of the most significant changes in the universe's character throughout its entire history. As the universe continued to expand and dark energy became increasingly dominant, the rate of galaxy mergers began to decline dramatically. The peak merger epoch ended roughly 6 billion years ago, and since then, the universe has been settling into an increasingly quiet and stable configuration where major merger events become progressively rarer. This decline in merger activity has profound implications for star formation throughout the universe. Galaxy collisions are among the most effective mechanisms for triggering bursts of new star formation as they compress gas clouds and drive material toward galaxy centers where it can fuel stellar birth. As merger rates have declined, so too has the overall rate of star formation throughout the cosmos. We're currently living in a universe that's past its peak stellar productivity, entering a long decline phase where new star formation becomes increasingly uncommon. The cosmic timeline revealed by galaxy collision rates also shows us that we're living in what might be called the aftermath era of cosmic evolution. Most of the major construction work is complete, and the universe is now dominated by the maintenance and slow dissolution of existing structures rather than the rapid assembly of new ones. This doesn't mean that galaxy mergers have stopped entirely. Our own future collision with Andromeda proves otherwise, but such events are becoming increasingly rare as cosmic expansion carries galaxy groups farther apart and reduces the likelihood of new encounters. Understanding this timeline has also revealed the crucial role played by what astronomers call the Great Attractor, one of the most mysterious and influential structures in our cosmic neighborhood. The Great Attractor is a massive gravitational anomaly located roughly 200 million light-years away, behind the plane of the Milky Way, making it difficult to study directly. This invisible cosmic giant contains the gravitational influence of tens of thousands of galaxies and is pulling our entire local group, along with thousands of other galaxies, toward it at speeds of several hundred kilometers per second. The Great Attractor represents one of the largest scale motions in our cosmic neighborhood and provides crucial evidence for how large-scale structure formation has proceeded throughout the universe's history. The fact that we're being pulled toward this massive concentration of matter demonstrates that the hierarchical assembly process isn't complete. Even today, smaller structures, like our local group, are slowly falling toward larger ones, in a process that will continue for billions of years to come. This ongoing motion toward the great attractor is part of a larger pattern of cosmic flows that reveals the underlying dark matter structure of the universe. Galaxies throughout the observable cosmos are moving not just due to cosmic expansion, but also due to gravitational attraction toward massive concentrations of dark matter called attractors. These flows trace out the cosmic web, the largest scale structure in the universe, consisting of filaments of dark matter connecting massive nodes where galaxy clusters form. The cosmic web represents the ultimate expression of hierarchical structure formation, where the tiny density fluctuations present in the early universe have grown over billions of years into the complex network of filaments, nodes, and voids that dominate the universe's large-scale architecture. Galaxy collisions occur preferentially along these filaments and at the intersections where they meet, reflecting the fundamental role that the cosmic web plays in determining where and when galactic encounters take place. Studies of galaxy collision rates at different cosmic epochs have revealed how this cosmic web has evolved over time. In the early universe, the web was much denser and more connected, with shorter distances between nodes and more opportunities for galaxy interactions along the connecting filaments. As the universe has expanded, the filaments have been stretched, and the nodes have become more isolated, leading to the declining merger rates we observe today. The evolution of the cosmic web also determines the future timeline of galaxy collisions throughout the universe. Computer simulations that follow cosmic evolution billions of years into the future show that the web will continue to stretch and fragment as dark energy drives accelerating expansion. Eventually, the filaments connecting different nodes will be stretched so thin that they effectively break, leaving galaxy clusters as isolated islands in an increasingly empty universe. This future evolution has dramatic implications for the long-term fate of galaxy formation and stellar birth throughout the cosmos. As the cosmic web fragments and galaxy groups become isolated, the supply of new material for galaxy growth will be cut off. Without fresh gas and small satellite galaxies falling in along cosmic web filaments, large galaxies will gradually exhaust their star-forming material and settle into a quiet old age dominated by low-mass, long-lived stars. The timeline revealed by galaxy collision studies also shows that different regions of the universe are at different stages of this evolutionary process. While our local group is still experiencing active evolution with the upcoming Milky Way-Andromeda merger, other regions of the universe have already reached more advanced stages where major merger activity has essentially ceased. The most massive galaxy clusters, which formed earliest in cosmic history, are now dominated by old elliptical galaxies with very little ongoing star formation, providing a preview of what the entire universe may look like in the far future. Perhaps most remarkably, the collision timeline reveals that we're living at a very special time in cosmic history, what astronomers sometimes call the stelliferous era, when star formation is still active throughout the universe but has passed its peak. This era, which began roughly 1 billion years after the Big Bang and will continue for perhaps 1 trillion years, represents just a tiny fraction of the universe's ultimate lifespan. But it's the only epoch when complex chemistry, planetary formation, and potentially life itself are possible on cosmic scales. The galaxy collision timeline also provides crucial insights into the ultimate fate of cosmic structure itself. As merger rates continue to decline and dark energy becomes increasingly dominant, We're heading toward an era that cosmologists call the degenerate era, when star formation will have essentially ceased throughout the universe, and only the longest-lived, lowest-mass stars will continue to shine. Eventually, even these stars will exhaust their fuel and die, leaving behind white dwarfs, neutron stars, and black holes as the only remaining sources of energy in an increasingly cold and dark universe. The final chapter in this cosmic timeline will be written by the supermassive black holes that reside at the centers of most large galaxies. Galaxies. During galaxy mergers, these black holes eventually spiral together and merge in cataclysmic events that produce gravitational waves and briefly outshine entire galaxies. As the universe continues to evolve and galaxy mergers become increasingly rare, these black hole mergers will become the dominant source of energy release in the cosmos, providing the final fireworks in an otherwise dying universe. Understanding this cosmic timeline through galaxy collisions has given astronomers unprecedented insight into both the universe's past and its future, revealing that we're living in a remarkable epoch when cosmic structure formation is winding down but hasn't yet ceased entirely. The upcoming collision between the Milky Way and Andromeda represents one of the last major merger events that will occur in our cosmic neighborhood, marking the end of an era that began with the first galaxy formation over 13 billion years ago. This collision timeline, decoded through careful observations of galaxy interactions throughout cosmic history, tells the story of a universe that has evolved from a chaotic construction zone into an increasingly ordered and ultimately dying cosmic ecosystem, with galaxy collisions serving as both the drivers of past evolution and the predictors of our cosmic destiny. As we peer into the cosmic crystal ball revealed by galaxy collision studies, we're about to explore perhaps the most profound and mind-bending chapter of our story: the ultimate implications of galactic mergers for the far future of the universe itself. What galaxy collisions tell us about the cosmos stretches far beyond the spectacular formation of Milkomeda in 4.5 billion years. They're revealing the final chapters of cosmic evolution, painting a picture of the universe's ultimate destiny that spans timescales so vast they make the entire history of life on Earth seem like a fleeting moment. This is the story of how the gravitational dances we observe today will write the final pages of reality itself, determining whether the universe ends in fire, ice, or something even more extraordinary. The formation of Milkomeda, the merged galaxy that will result from the Milky Way and Andromeda collision, represents just the opening act of a cosmic drama that will unfold over timescales that challenge human comprehension. When our two spiral galaxies finally settle into their new configuration, roughly 6 billion years from now, the resulting elliptical galaxy will be a fundamentally different cosmic entity than either of its parent galaxies. Computer simulations predict that Milkomeda will contain roughly 1 trillion stars, making it one of the more massive galaxies in our cosmic neighborhood. But its formation will trigger changes that extend far beyond simple arithmetic addition of stellar populations. The merger process will compress vast reservoirs of gas that currently exist in both galaxies, triggering what astronomers call a starburst event, a period when new star formation occurs at rates tens or even hundreds of times faster than normal. This cosmic fireworks show will be visible from billions of light years away, temporarily making Milkomeda one of the most luminous objects in our local cosmic neighborhood. But this burst of activity will also consume most of the remaining star-forming material in both galaxies, essentially using up the raw ingredients needed for future stellar birth in one spectacular cosmic celebration. The implications of this consumption of star-forming material extend far into the future because it represents the end of major star formation in our cosmic neighborhood. After the Milkomeda starburst fades, there will be no other nearby galaxies to provide fresh material for continued stellar birth. The smaller satellite galaxies that orbit both the Milky Way and Andromeda will likely be disrupted or consumed during the merger process, their gas and stars scattered throughout the new galaxy's extended halo. This means that Milkomeda will gradually settle into a quiet old age, dominated by increasingly dim and cool stars as the bright, massive stars formed during the merger burn out and die. But Milkomeda's formation is just one example of a process that will be repeated throughout the universe over the next several trillion years. Galaxy mergers will continue to occur within gravitationally bound groups and clusters, gradually combining smaller systems into fewer and fewer massive galaxies. Each merger will trigger its own starburst and consume more of the universe's finite supply of star-forming gas, bringing the cosmos one step closer to the end of the stelliferous era, the current epoch when active star formation illuminates the universe. The timeline for this process is almost incomprehensibly long. While major mergers within galaxy groups will continue for tens of billions of years, the formation of new stars will persist for roughly 1 trillion years, as the universe slowly consumes its remaining reservoirs of hydrogen and helium. During this extended twilight phase, the universe will be dominated by increasingly old and cold stellar populations, with new star formation becoming progressively rarer until it eventually ceases entirely. As star formation winds down throughout the cosmos, the universe will enter what cosmologists call the degenerate era, when stellar remnants, white dwarfs, neutron stars, and black holes begin to dominate the cosmic inventory. During this era, which will last for roughly 1 quintillion years, the universe will be a much darker and colder place than today, illuminated primarily by the fading glow of white dwarf stars that can persist for trillions of years before finally cooling into invisible black dwarfs. But even during this seemingly quiet era, galaxy mergers will continue to play a crucial role in cosmic evolution, though at increasingly slow rates as cosmic expansion carries galaxy groups farther apart. The mergers that do occur will primarily involve the coalescence of stellar remnants rather than active star formation, gradually building up more massive white dwarfs and neutron stars through accretion and direct collision. Some of these mergers will be spectacular events, producing Type 1a supernovae, when white dwarfs accrete enough material to exceed their stability limit, or creating gamma ray bursts, when neutron stars collide and merge. The supermassive black holes that reside at the centers of most large galaxies will become increasingly important players in this far future universe. As galaxies merge, their central black holes will inevitably spiral toward each other, eventually coalescing in cataclysmic events that release more energy in gravitational waves than all the stars in the observable universe emit in electromagnetic radiation. These black hole mergers, detected today by instruments like LIGO and Virgo, represent some of the most violent events possible in the universe, briefly warping spacetime so dramatically that the waves can be detected across billions of light years. The discovery of gravitational waves from merging black holes has opened up an entirely new window into cosmic evolution. allowing astronomers to study processes that would be completely invisible to conventional telescopes. As galaxy mergers become increasingly rare in the far future, black hole coalescence will become the dominant source of energy release in the universe, providing brief but spectacular fireworks shows in an otherwise darkening cosmos. The growth and merger of supermassive black holes also has profound implications for the ultimate fate of galactic structure itself. As these cosmic monsters continue to accrete material and merge with each other, they will gradually consume increasing fractions of the mass in their host galaxies. In the extremely far future, hundreds of trillions of years from now, galactic evolution may be dominated by the slow consumption of stellar material by ever-growing supermassive black holes, gradually converting the organized structure of galaxies into the chaotic environment surrounding massive black holes. Even more dramatic changes await the universe if current theories about dark energy prove correct. The mysterious force that's currently accelerating cosmic expansion shows no signs of weakening, and if it continues to strengthen over time, it could lead to what cosmologists call the Big Rip, a scenario where the expansion of space eventually becomes so rapid that it overcomes gravity on all scales, tearing apart galaxy clusters, individual galaxies, solar systems, and ultimately, even atoms themselves. In the Big Rip scenario, which could occur roughly 22 billion years from now if dark energy continues to strengthen, the final galaxy mergers would happen against a backdrop of increasingly violent cosmic expansion. Galaxy groups, like our local group, would be the last gravitationally bound structures to survive, as expansion eventually overcomes even the strongest gravitational bonds. The final moments before the Big Rip would see individual galaxies stretched apart as space expands faster than light can travel between their constituent stars, followed by the dissolution of solar systems, planets, and finally, the atomic structure of matter itself. Alternatively, if dark energy remains constant or eventually weakens, the universe faces a different but equally dramatic fate in the form of heat death. In this scenario, cosmic expansion continues forever, but at a gradually decreasing rate, allowing gravitational processes to continue operating for incredibly long periods. Galaxy mergers would persist for hundreds of trillions of years, gradually building up fewer and fewer but increasingly massive galactic structures as smaller systems are consumed by larger ones. The heat death scenario leads to what cosmologists call the black hole era, beginning roughly 100 quintillion years from now, when stellar evolution has run its course and black holes become the dominant objects in the universe. During this era, the largest supermassive black holes, grown massive through eons of galaxy mergers and stellar consumption, will slowly evaporate through Hawking radiation, a quantum mechanical process that causes black holes to gradually lose mass by emitting elementary particles. The timescales involved in black hole evaporation are almost beyond comprehension. A black hole with the mass of our Sun would take longer than the current age of the universe raised to the 67th power to completely evaporate. Supermassive black holes formed through galaxy mergers, containing billions of times the Sun's mass, would persist for timescales that dwarf even these incomprehensible numbers. The universe, during the black hole era, would be a cold, dark place where isolated black holes slowly shrink through Hawking radiation, occasionally producing brief flashes of energy as they consume the few remaining particles drifting through the cosmic void. The final phase of cosmic evolution, assuming the heat death scenario, would be the dark era, beginning when even the largest black holes have finally evaporated away. This era would last essentially forever, with the universe consisting of nothing but elementary particles, electrons, positrons, neutrinos, and photons scattered throughout ever-expanding space at temperatures just barely above absolute zero. The organized complexity that characterizes today's universe, from galaxies and stars to planets and potentially life itself, would be nothing but a distant memory encoded in the extremely dilute quantum vacuum of a maximally entropic cosmos. Yet even in these far future scenarios, the role of galaxy collisions remains crucial for understanding how cosmic evolution proceeds. The timing and frequency of galactic mergers determine how quickly the universe consumes its star-forming material, how rapidly supermassive black holes grow through coalescence, and how long organized galactic structures can persist against the relentless expansion of space. Recent observations of galaxy mergers at different cosmic epochs have allowed astronomers to calibrate models of far future evolution with unprecedented precision. By studying how merger rates have changed over the universe's 13.8 billion year history, scientists can extrapolate these trends billions and trillions of years into the future, creating detailed timelines for the end of star formation, the growth of black holes, and the ultimate fate of cosmic structure. Perhaps most remarkably, galaxy collision studies have revealed that we're living during an incredibly special and brief period in cosmic history. The stelliferous era, characterized by active star formation and complex galactic evolution, represents less than 1% of the universe's total lifespan if current cosmological models are correct. The vast majority of cosmic time will be spent in the much quieter and darker eras that follow, when the spectacular processes we observe today, star formation, galaxy mergers, and the complex interplay between dark matter and ordinary matter, will be nothing but ancient history. This realization has profound implications for our understanding of cosmic evolution and the potential for complex phenomena like life to exist throughout the universe's history. The window of opportunity for the complex chemistry required for biological processes appears to be cosmically brief, concentrated in the current epoch when stars are actively forming and creating the heavy elements necessary for planetary formation and biochemistry. The study of galaxy collisions has thus revealed not just the mechanical processes that shape cosmic structure, but the fundamental timeline that governs the possibility for complexity and organization in the universe itself. From the first merger events that built the galaxies we see today, to the final black hole coalescences that will mark the end of gravitational dynamics, galactic interactions represent the heartbeat of cosmic evolution, a rhythm that started with the first collapse of dark matter halos in the early universe and will continue until the last black holes evaporate into the cold, empty expanses of a maximally dilute cosmos. As we contemplate these vast timescales and dramatic transformations, galaxy collisions emerge not just as spectacular astronomical phenomena, but as the fundamental processes that connect the universe's explosive birth in the Big Bang to its quiet death in heat or catastrophic destruction in the Big Rip. Understanding these cosmic dances allows us to situate our own moment in cosmic history and appreciate just how remarkable and fleeting the current epoch of active galactic evolution truly is in the vast sweep of cosmic time. As we reach the end of our cosmic journey through the gravitational ballet of galaxy collisions, it's time to step back and absorb the full magnitude of what we've discovered together. What began as a simple question about why some galaxies are approaching us in an expanding universe has unveiled nothing less than the complete biography of reality itself, a story that stretches from the first moments after the Big Bang to the final death throes of the cosmos trillions of years in the future. Galaxy collisions have emerged not just as spectacular astronomical phenomena, but as the Rosetta Stone that allows us to decode the universe's deepest secrets and understand our own place in the vast sweep of cosmic time. The journey we've taken reveals that everything we thought we knew about the cosmos has been transformed by studying these cosmic dances. When Edwin Hubble first discovered that spiral nebulae were actually distant galaxies in the 1920s, he opened a window into a universe far larger and more dynamic than anyone had imagined. But it was only through decades of studying how these galaxies interact, merge, and evolve that we've come to understand the true nature of cosmic evolution. Galaxy collisions have taught us that the universe isn't a static collection of distant lights, but a living, breathing cosmic ecosystem where structures grow, transform, and eventually die through gravitational interactions that unfold over billions of years. Perhaps the most profound revelation from our exploration is the discovery that we live in a universe dominated by invisible components that shape everything we see. Dark matter, making up 85% of all matter, provides the gravitational scaffolding that determines when and how galaxy collisions occur. Without this invisible cosmic architecture, galaxies would never have formed in the first place, and the spectacular merger events we observe would be impossible. Dark energy, even more mysterious than dark matter, drives the accelerating expansion that will ultimately determine whether galaxy collisions continue forever or eventually cease as cosmic structures become isolated islands in an ever-expanding void. The cosmic timeline revealed by galaxy collision studies has fundamentally changed our perspective on time itself. We've learned that we're living during an incredibly brief and special epoch in the universe's 13.8 billion year history, a cosmic moment when star formation is still active, when complex galactic structures continue to evolve, and when the heavy elements necessary for planets and life are being created in stellar furnaces throughout the cosmos. This stelliferous era represents less than 1% of the universe's total lifespan, making our current moment in cosmic history extraordinarily precious and rare. Looking ahead to our own galactic future, the approaching collision with Andromeda serves as both a preview of cosmic evolution and a profound reminder of the scales involved in cosmic change. In 4.5 billion years, when these two spiral galaxies begin their billion-year merger dance, the Earth may no longer exist as we know it. The Sun will be entering the final phases of its stellar evolution, and any civilizations that witness the event will see a night sky transformed beyond recognition. Yet this spectacular merger represents just one chapter in a cosmic story that will continue for timescales that dwarf the entire history of life on Earth. The formation of Milkomeda will mark both an ending and a beginning. The end of our galaxy's independent existence as a spiral galaxy, and the beginning of a new cosmic entity that will persist for trillions of years into the future. This merger will trigger massive bursts of star formation that temporarily illuminate our cosmic neighborhood, but it will also consume most of the remaining raw materials for future stellar birth, bringing our region of the universe one step closer to the quiet old age that awaits all galactic structures. What makes galaxy collision studies so remarkable is how they've revealed the interconnectedness of cosmic evolution across vast scales of space and time. The same gravitational processes that govern the merger of dark matter halos in computer simulations also determine the fate of individual galaxies, the growth of supermassive black holes, and the ultimate architecture of the cosmic web that spans billions of light years. Understanding these connections has given us unprecedented insight into how the universe evolved from the relatively smooth conditions shortly after the Big Bang into the complex hierarchy of cosmic structures we observe today. The role of supermassive black holes in cosmic evolution, revealed through their behavior during galaxy mergers, has opened entirely new chapters in our understanding of how cosmic structures grow and evolve. The discovery that these cosmic monsters can merge and produce gravitational waves detectable across billions of light years has provided direct evidence for some of the most extreme predictions of Einstein's general relativity. As galaxy mergers become increasingly rare in the far future, these black hole coalescences will become the dominant source of energy release in the universe, providing the final fireworks in an otherwise darkening cosmos. Perhaps most humbling is the realization that the spectacular processes we observe today, active star formation, dynamic galactic interactions, and the complex interplay between ordinary and dark matter, represent a brief flowering of cosmic complexity that will gradually fade as the universe evolves toward simpler, more dispersed states. The heat death scenario, where the universe eventually reaches maximum entropy with all available energy distributed uniformly throughout ever-expanding space, represents the ultimate victory of cosmic expansion over gravitational organization. Yet even in contemplating these vast timescales and ultimate cosmic fates, galaxy collision studies have revealed reasons for cosmic optimism. The merger processes that will eventually end active star formation also extend the universe's stellar lifetime by recycling gas and triggering new generations of stellar birth. Each galaxy collision creates opportunities for planets to form around newly created stars, potentially extending the window for complex chemistry and biological evolution far beyond what would be possible in isolated galactic systems. The precision with which we can now predict cosmic evolution represents one of the greatest triumphs of human scientific understanding. Using nothing more than careful observations of distant galaxies and the fundamental laws of physics, we've mapped out the universe's future with remarkable accuracy, from the detailed timeline of the Milky Way-Andromeda merger to the ultimate fate of cosmic structure billions of years from now. This predictive power demonstrates the deep connections between local physical processes and cosmic evolution, showing that the same principles that govern everyday phenomena on Earth also determine the destiny of galaxies and the universe itself. Looking toward the future of astronomical discovery, galaxy collision studies are entering a golden age of observation and understanding. The James Webb Space Telescope is already revealing galaxy mergers in the early universe with unprecedented clarity, showing us cosmic construction in action during the peak epochs of galactic assembly. Future missions, like the Euclid Space Telescope, will map the cosmic web in 3 dimensions, revealing how dark matter guides galactic evolution across cosmic time. Ground-based gravitational wave detectors continue to detect black hole mergers with increasing sensitivity, providing direct measurements of the cosmic collision rate and its evolution over billions of years. These ongoing and future observations will refine our understanding of cosmic evolution and may reveal surprises that challenge our current models. The nature of dark matter and dark energy remains mysterious despite their dominant roles in shaping cosmic structure, and galaxy collision studies may provide crucial clues about the fundamental physics underlying these enigmatic components of the universe. Understanding how galaxies formed and evolved in the early universe, revealed through observations of high redshift mergers, will test our models of cosmic evolution and potentially reveal new physics operating under extreme conditions. The study of galaxy collisions has also revealed the remarkable role that cosmic accidents and contingencies play in shaping the universe we observe. The specific timing and geometry of galactic encounters can dramatically affect their outcomes, determining whether mergers trigger starbursts or quench star formation, whether spiral structure survives or is destroyed, and whether central black holes grow rapidly or remain dormant. These contingent factors remind us that while the large-scale evolution of the universe follows predictable patterns, the detailed history of individual cosmic structures depends on countless chance encounters and near misses that occurred over billions of years. This interplay between cosmic determinism and contingency extends to the possibilities for life and intelligence throughout the universe. Galaxy mergers can trigger star formation that creates new planetary systems, but they can also disrupt existing planetary environments through gravitational perturbations and increased radiation from active galactic nuclei. Understanding how these processes affect the habitability of cosmic environments over time provides crucial context for astrobiology and the search for life beyond Earth. The cosmic perspective revealed by galaxy collision studies also illuminates the remarkable nature of our current moment in cosmic history. We exist during a brief epoch when the universe contains both the complex structures necessary for stellar evolution and planetary formation, and the stable galactic environments needed for long-term biological evolution. This cosmic sweet spot will gradually disappear as galaxy mergers consume star-forming material and cosmic expansion isolates galactic structures, making our current era of cosmic complexity a fleeting moment in the vast timeline of cosmic evolution. From a philosophical perspective, understanding galaxy collisions and cosmic evolution raises profound questions about the nature of cosmic purpose and meaning. Are we witnessing a universe that's gradually winding down from an initial burst of creative energy? Or are we seeing ongoing creative processes that continue to generate new forms of cosmic complexity? The answer may depend on whether future discoveries reveal new physics that can reverse cosmic expansion, halt the growth of cosmic entropy, or enable entirely new forms of cosmic organization that we can't currently imagine. The technological capabilities that have enabled our understanding of galaxy collisions, from Hubble's pioneering observations to modern gravitational wave detectors, represent remarkable achievements of human ingenuity and international scientific cooperation. These discoveries required decades of patient observation, theoretical development, and technological innovation, demonstrating humanity's capacity to understand phenomena that occur on scales vastly larger than our direct experience and over timescales that dwarf human civilization. As we continue to probe deeper into space and time with ever more sophisticated instruments, galaxy collision studies will undoubtedly reveal new surprises and deepen our understanding of cosmic evolution. The universe has consistently proven more strange, beautiful, and complex than our theoretical predictions, and there's every reason to expect that future observations will continue to challenge and expand our cosmic perspective. And so, we reach the end of our incredible journey through the cosmic dance of galaxies, a journey that has taken us from the first puzzling observations of missing mass in the 1930s to mind-bending predictions about the ultimate fate of reality itself. What we've discovered together is nothing short of extraordinary. Galaxy collisions aren't just spectacular cosmic fireworks. They're the key that unlocks the universe's deepest secrets and reveals our place in the grand story of cosmic evolution. We've learned that we live in a universe far stranger and more magnificent than our ancestors ever imagined. A cosmos where invisible dark matter provides the gravitational scaffolding for everything we see, where mysterious dark energy drives an accelerating expansion that will ultimately determine the fate of all cosmic structure, and where the spectacular merger events we observe today represent the final chapters of active cosmic construction in our corner of the universe. Perhaps most remarkably, we've discovered that we're living during an incredibly special moment in cosmic history. The current epoch of active star formation, dynamic galactic evolution, and complex cosmic chemistry represents just a brief flowering of cosmic complexity that will gradually fade as the universe evolves towards simpler, more dispersed states. We're witnessing the universe during its prime, a cosmic moment when planets can form, heavy elements are being created, and the conditions for life and intelligence exist throughout the cosmos. The approaching collision between our Milky Way and the Andromeda Galaxy serves as both our cosmic destiny and a perfect metaphor for the universe itself. This spectacular merger, destined to occur in 4.5 billion years, will create something entirely new, Milkomeda, while transforming and ultimately ending the independent existence of both parent galaxies. It's a reminder that even on cosmic scales, nothing lasts forever, but destruction often leads to new forms of creation and beauty. What makes this entire story so incredible is that we figured it all out through human curiosity, scientific dedication, and our remarkable ability to decode the universe's secrets through careful observation and mathematical analysis. Every insight about dark matter's role in galactic evolution, every prediction about our cosmic future, every timeline for the universe's ultimate fate, it all emerged from our species' relentless quest to understand the cosmos and our place within it. This is exactly the kind of mind-expanding exploration we live for here at the Lazy Cosmos, taking the universe's most profound mysteries and making them accessible without sacrificing their incredible depth and beauty. If this cosmic journey has left you as amazed and humbled as it has left me, make sure you're subscribed to the Lazy Cosmos and ring that notification bell, because we're just getting started on our quest to understand the universe's most extraordinary secrets. The story of galaxy collisions is ultimately the story of everything. From the invisible dark matter that shapes cosmic structure to the ultimate fate awaiting all the stars, planets, and potentially civilizations throughout the cosmos. We've seen how the gravitational dance of galaxies connects the smallest quantum processes to the largest cosmic structures, revealing a universe that's simultaneously more interconnected and more vast than we ever dared imagine. What fascinates you most about our cosmic future? The role of invisible dark matter in choreographing galactic evolution? The mind-bending timescales involved in cosmic evolution? The possibility that we're living during the universe's brief moment of maximum complexity? Share your thoughts in the comments below. Your questions and insights often inspire our next cosmic adventures, and there's nothing I love more than exploring the universe's mysteries together with fellow cosmic explorers. As we continue to develop more powerful telescopes and detection methods, from the James Webb Space Telescope revealing galaxy formation in the early universe to gravitational wave detectors catching black holes in the act of merging, we're entering a golden age of cosmic discovery. Each new observation adds another piece to the cosmic puzzle, helping us understand not just how the universe works, but why it works the way it does. The universe has been writing its autobiography in starlight and gravity for nearly 14 billion years, and we've finally learned how to read it. Galaxy collisions have given us the cosmic Rosetta Stone, allowing us to decode everything from the nature of dark matter to the ultimate fate of space and time itself. We've discovered that we're part of a universe that's both incredibly ancient and incredibly young, both unimaginably vast and remarkably intimate, both utterly indifferent to our existence and absolutely essential for our presence. Thank you for joining me on this extraordinary journey through the cosmic dance of galaxies. Remember, every time you look up at the night sky, you're seeing a snapshot of cosmic evolution in action. Ancient light from distant suns, members of galaxies that are slowly approaching their own cosmic destinies in the great dance of gravitational attraction and cosmic expansion. The story continues with every new discovery, every new observation, and every moment of wonder as we contemplate our place in this magnificent cosmic tapestry. Until our next journey together, keep looking up, keep asking questions, and remember that the universe's greatest secrets are still waiting to be discovered. The cosmic dance continues, and we have front row seats to the greatest show in existence. This has been The Lazy Cosmos, where we explore the universe's biggest mysteries without getting lost in the complexity. The cosmos is calling, and our adventure is just beginning.